Hi, hello and welcome everyone. In this video, we are just going to interface simplest form of analog sensor, that is variable resistor, with PIC16F877A microcontroller by programming in MPLAB X IDE. Let's get started. So for starting off, we are just going to learn these things in this video. That is, at the beginning, we will be learning the working principle of variable resistor, and following that, we will be learning the ADC module functioning in PIC16F877A microcontroller, and following that, we will be learning how we can interface variable resistor to that microcontroller, and finally, we will be displaying the step value that we received from the variable resistor onto the LCD with the help of a microcontroller, and finally we will be achieving this result. So let's get started off with the first thing. So for understanding the working principle of variable resistor, I have built a Proteus simulation circuit right over here. So with this circuit, we are just going to learn the working principle of variable resistor. So basically, variable resistors are nothing but simple resistors whose resistance value can be varied by rotating the knob available in the variable resistor, either in clockwise or in anti-clockwise direction. So this is a basic circuit with the help of which you can receive voltage signals from variable resistor. That is, usually variable resistors will be having three terminals, one on the left, second on the right, and third one is available in the middle terminal. To the left terminal, I have connected ground of the circuit, and to the rightmost terminal, I have connected the positive 5 volt signal. And to the middle terminal, which is the sensing point for the microcontroller, I have connected a voltmeter. So usually here in the middle terminal of the variable resistor, we will be connecting the analog pin of the microcontroller, using which we will be sensing and measuring the voltage signal as an analog source. So this is the sensing point, that is the middle terminal of variable resistor, and for now I have connected a voltmeter for testing the voltage signal, that is DC voltmeter. Now when I turn on the simulation, you can see my voltmeter is showing the reading 0 volt, since the potentiometer knob is available in the 0%, that is towards the extreme left side direction. And now when I try to rotate the knob of the potentiometer towards the other end, you can see there is variation in voltage signal. And when I place the knob of the potentiometer or variable resistor in the other extreme end, that is towards the right side, you can see I am getting a 5 volt signal in this voltmeter. That is nothing but the voltage signal provided right over here. So this is the concept. The resistance of the variable resistor varies based on the knob rotation of the potentiometer or variable resistor, and based on the resistance value, I will be getting the voltage signal in the middle terminal. So when I place the knob in the 0%, that is towards the extreme ground end, I will be getting a 0 volt signal, and when I place the knob in the extreme right end, that is towards the 5 volt signal, I will be getting a 5 volt in the middle terminal, and when I place the knob in the 50% of the potentiometer value, I will be getting 50% of the voltage signal provided over here. That is, I have provided a 5 volt signal right over here. That is why I am getting a 2.5 volt signal right over here. And when I place the knob in the 10% of the potentiometer value, I will be getting 10% of the 5 volt, that is nothing but 0.5 volt. Similarly, when I place the knob in the 80% of the potentiometer, I will be getting 4 volt signal, which is 80% of 5 volt signal. So based on the knob rotation of the variable resistor, we will be getting a varying voltage signal in the middle terminal of variable resistor. So using the ADC peripheral of any microcontroller, you can read this voltage signal coming from variable resistor. And these kinds of variable resistors are most widely useful in applications like volume control, speed control, etc. So for now, I hope you understood the working principle of variable resistor. Based on the knob rotation of the variable resistor, we will be getting voltage signals in the middle terminal of the variable resistor. And now let's move on to the next part of the video, that is for understanding how a ADC module in the PIC16F877A microcontroller works. The microcontroller that we are going to use in this video is PIC16F877A, and the analog channels available in this microcontrollers are RA0, RA1, RA2, RA3 and finally RA5. And other than these 5 pins from port A, we are having 3 pins from port E, that is RE0, RE1 and RE2. So totally we are having 8 analog channels in this microcontroller starting from AN0 to AN7. These 8 pins are analog channels of this microcontroller for interfacing any analog voltage type sensors to this microcontroller. And as per one of my previous video where I have explained you about the working principle of ADC peripheral of any microcontroller, the main functionality of ADC peripheral of the microcontroller is converting analog signal format into digital format. That is, the analog DC voltage level will be converted into equivalent step value inside the ADC peripheral of the microcontroller. And the range of step values that we will be reading from the ADC peripheral will be depending on the resolution of the ADC peripheral available inside the microcontroller. And the ADC module available in this microcontroller is having the resolution of 10-bit, which means it will be having the range of step values between 0 to 1023. So this 1023 is nothing but 0 to 2 to the power 10 minus 1, that is 1023. For example, if you are operating your microcontroller in a 5 volt power source, the maximum step value 1023 will be provided for the 5 volt signal in the analog channel, and if you are providing a 0 volt signal in the same analog channel, we will be receiving and reading the step value in the ADC channel to be 0. So this is how the ADC will be functioning. For the maximum voltage provided in the V reference pin, we will be getting the maximum step value of 1023 in this microcontroller ADC channel. And the intermediate voltage values between 0 to 5 volt will be having the equivalent step values within the range 0 to 1023. So this is how the ADC peripheral available in the microcontroller will be providing us with the step values corresponding to the voltage provided in the particular ADC channel. So this is how the ADC will be functioning. And if you are operating the microcontroller with a 3.3 volt signal, I will be getting this 1023 step value for the provided 3.3 volt signal in the analog channel of the microcontroller. And for calculating the step size, this is the formula used. You can see clearly step size is equal to VCC divided by 2 to the power n minus 1, where VCC is the power of the microcontroller, which in my case is 5 volt signal, which has been substituted in this formula. And this small n in this 2 to the power n means the resolution of the ADC. So our ADC is having the resolution of 10 bit, as I said. So 2 to the power 10 is nothing but 1024, which has been substituted right over here, and minus 1, which will provide me 1023. And finally, when you solve this equation, you will be getting the result to be 4.8 millivolt. So from this value, you can conclude that 4.8 millivolt is the least readable voltage signal by the ADC module of this microcontroller. So the step size determines the least readable ADC voltage value for the particular ADC module of the microcontroller. So this is the formula for calculating the step size of the ADC channel of the microcontroller. and the least voltage that can be read from the ADC module of this microcontroller is 4.8875 millivolt. So below this reading, the controller will not be able to read the step value, so it will be showing you 0, and once it reaches 4.8875 millivolt and above, it will be showing us the step value to be 1. And 4.8 millivolt is the voltage difference between each step of the ADC module of the microcontroller. So this is how you can calculate the step size of the ADC module of the microcontroller. And here you can clearly see I am operating the microcontroller with the reference voltage of 5 volt signal, and if you are operating the microcontroller with a 3.3 volt signal, the value you need to substitute here is 3.3, and you will be getting a different step value based on the voltage reference provided for the microcontroller. So make sure to substitute the correct voltage source available for your microcontroller right over here for calculating the step size. And in addition to that, ATCON 0 and ATCON 1 are the control registers associated with the ADC module of the microcontroller. In addition to that, we are having two different registers, address L and address H, which are the data registers useful for storing 10-bit ADC data result. Since we are having a 10-bit value, we have been provided with two different 8-bit registers. One is address H and other one is address L. So the data alignment of the 10-bit data can be selected from the software side itself depending on a particular bit available in the ATCON 0 and ATCON 1 that we will see later in this video. So that's all about the ADC peripheral available in this microcontroller. Let's move on to the next part of the video, that is the third topic, interfacing variable resistor with PIC16F877A microcontroller. Now I am just going to create the Proteus simulation circuit for simulating our project first. I am opening the Proteus 8 professional software. Click on the schematic capture tab and then click on the components mode and then click on this PIC devices icon right over here, and here type in the microcontroller name PIC16F877A and double click on this microcontroller for selecting the microcontroller, and then we require LCD for this project. Type in LM016L, which is the 16x2 alphanumeric LCD. Double click on this LCD for selecting this too, and further we require pot, which is the potentiometer or variable resistor. Here you can select this pot HG active device. Double click on this and you can see the devices you have selected has been listed out right over here. That's all about the devices required for our project. Close this tab and I'm just going to place the microcontroller somewhere right over here, and I'm just going to connect the potentiometer or variable resistor to RS0, and the LCD I will be connecting it to port B of the microcontroller. And for this potentiometer I require 5 volt signal and ground, so I'm just going to select that. Click on the terminals mode icon right over here and then select the power, which is the power source, and here is the ground. I'm just going to place the ground right over here. Now I'm just going to connect the ground to one end of the potentiometer and power supply to another end of the variable resistor. Now, and then the terminal of voltage output of the variable resistor, that is the middle terminal, I'm just going to connect it to RA0, that is the analog channel 0 of the microcontroller. Double click on this power source and type in plus 5 volt. So this is a 5 volt power source. And regarding the LCD connections, as usual, as we did in the interfacing of LCD with PIC16F877A microcontroller in 4-bit mode, I am just going to connect RB0 to D4 of the LCD, D5 to RB5, RB6 to D6, D7 to RB7. And regarding the RS pin, I am just going to connect it to RB0, RW will be connected to RB1 and enable will be connected to RB2, and RB3 will be left blank. And that's all about the circuit required for simulating this project. we have successfully connected the variable resistor to the analog channel 0 of the microcontroller, and for displaying the step value that we read from the analog channel, we have connected a LCD to port B of the microcontroller. Now I am just going to open the MPLAB X IDE for start writing the programming for this project. In this welcome page, you can either click on this new project icon, or you can click on this file tab and then click on new project. In this first tab, just select the standalone project inside the microchip embedded and then click on next. Here in the second tab of select device, you just want to select the microcontroller required. So in our case, the microcontroller required is PIC16F877A. Just type in the microcontroller name and then select the microcontroller. And after selecting that, click on next. And here in the select compiler tab, you just want to select the compiler that you want to work on. In my case, I'm just going to work on XC8 compiler, and then I'm just going to click on next. Here in the project name, you just want to provide a name for your project. So I'm just providing a particular name. And if you want to change the destination folder, just click on this browse and go to the respective destination where you want to store the project files, and select the folder and click on open. And then finally click on this finish button for creating the project. Here you can see the project has been created with the name that is provided by me, and in this source files of the project, just right click on this source files and hover over new and click on this main.c for creating the main.c file required for the project. In this tab, just click on finish. If you want to change the file name, you can change it right over here in this tab, and that's it. You can see this is the main.c file created for the project. And now you can start writing the programming logic required for running your microcontroller inside the void main available in the main.c file. So I'm just going to create a while of 1, which is the infinite loop, where you will be writing the repeatedly executable statements in the program, and above the while of 1 we will be writing the configuration statements which needs to be executed only once in the lifetime of the program. Now that we are ready for writing the logic for our microcontroller, before start writing the logic, we just want to set and provide the configuration bits for the microcontroller. For that, just click on this production tab and select this set configuration bits button. Here in this tab shown right below, you can select the configuration bits. Here in the F oscillator, just select the HS oscillator. Now I'm just turning off the watchdog timer, power up timer, and also I'm just turning off the brownout reset. For now, I'm just going to leave this low voltage in circuit serial programming enable bit on. Other than that, I'm just going to clear all the configuration bits. Then after setting the configuration bits, just click on the generate source code to output button. Here you can see this is the configuration lines generated by the MPLAB X IDE. I'm just going to copy these lines and I'm going to paste it right over here. That's all about the configuration bits required for running the microcontroller. Now you can start writing the logic in the void main provided by the main.c file. This is one of my previous lecture where I have interfaced 16x2 LCD with PIC16F877A microcontroller in 4-bit mode. So in that lecture we successfully interfaced 16x2 LCD with this microcontroller in 4-bit mode format. So this is the program that we wrote in that lecture. So in this lecture also I am just going to use the same LCD functions. So I am just going to copy all this program from this definition part till the main function. I'm just going to copy this and I'm going to delete this main function and I'm going to paste this right over here in this program. So here also you can see RS is connected to RB0, RW is connected to RB1 and enable is connected to RB2. And regarding the data lines, port B is used for the data lines, that is nothing but the port B MSP bits is useful for data lines. So that is done right over here. So we are just going to use the same LCD functions as we did in that lecture. So if you have not watched that lecture, you can go through that lecture by clicking on the link provided in the description of this video. That link will be directing you to a playlist of MPLAB X programming. So there you can find all the lectures associated with MPLAB X IDE. So now in this program you can see initially we are making all the pins of port B as output by providing 0x00 to TIS B, and we are initializing the LCD. And finally coming inside the void 1 and finally coming inside the while of 1, we are printing SM training in the first row first column of the LCD and academy in the second row first column of the LCD. So I am just going to delete this second line, I don't require this. And here in the first row first column I am just going to print port value. So it is having 1 2 3 4 5 6 7 8 9 10 characters. So I am changing the length of the string here to be 10, and that's it. Now when I build this project, you can see the build is successful. And regarding the logic of this program written right over here, it will print port value string from the first row first column of the LCD. And regarding all these functions, that is the LCD functions, LCD init, string, command and data functions, I am not going to explain it in this lecture. I have already done that in this lecture step by step. So you can go back to that lecture if you have not watched this lecture. Now coming to our programming logic, I am just going to dump this program onto this Proteus simulation microcontroller for viewing this output. Double click on this microcontroller and change the frequency to be 20 MHz. Click on this program file and go to the respective project folder where you have stored the project files. And inside the dist, default and production folder, select this hex file and click on open. And then click on OK. Now when I play the simulation, you can see the string port value has been printed from the first row first column of the LCD. So our LCD functions are working fine. Let's start writing the programming for configuring the ADC module and then for receiving the analog step value from the analog channel 0 of this microcontroller. So as I said, the registers associated for ADC peripherals are ADCON 0 and ADCON 1. So I am just going to open the datasheet of the PIC16F877A microcontroller. In this datasheet, just double click on this ADC module. Here you can find the registers useful for ADC peripheral. The first and foremost register is ADCON 0. As I said, this is the one of the control registers useful for configuring the ADC peripheral. So in this register, ADC S1, ADC S0 and ADC S2 are useful for defining the clock frequency for ADC peripheral. So here in this case, if I define these 3 bits to be 0, 0, 0, F oscillator divided by 2 will be the ADC clock. So F oscillator is nothing but the main system clock. Main system clock divided by 2 will be my ADC frequency for sampling the analog voltage signal. So I am just going to select the F oscillator divided by 8. So I just want to set the ADC S0 bit and I want to clear the ADC S1 bit along with ADC S2 bit. Here in this register we are having ADC S0 and S1, and ADC S2 is available in the ADCON 1 register right over here. So I just want to clear the ADC S2 and S1 and I want to set the ADC S0. So I'm just going to initialize the ADC starting from here. So ADCON 0 bits dot ADC S0 is equal to 1 and ADCON 0 bits dot ADC S1 is equal to 0. ADCON 0 bits dot ADCON 1 bits dot ADC S2 is equal to 0. So this will configure the ADC clock to be F oscillator divided by 8. So we have successfully configured the frequency for ADC peripheral of the microcontroller, and coming to the next part, we just want to turn on this bit for turning on the power for this ADC peripheral. You can see clearly here, when this bit is 0, AD converter module is shut off and consumes no operating current, and when this bit is 1, ADC converter module is powered up. So definitely we just want to set this bit on for using the ADC peripheral of the microcontroller. So I'm just going to set this bit to 1. ADCON 0 bits dot add on is equal to 1. Power up ADC module. And regarding these 4 bits, we will see a little bit later in this video. Now coming to the ADCON 1 register, here you can see there are 4 bits available in the LSB of this register, that is PCF G0 to PCF G3. So these 4 bits defines the port configuration of the ADC peripheral of the microcontroller. So if these 4 bits are provided with 0000, all the channels starting from AN7 to AN0 will be configured as analog channels. So in our case, as we did in the Protest simulation circuit, we have connected and used only RA0, which is nothing but AN0 of the microcontroller. So we require only AN0 to be configured as analog, and regarding all the other pins, we don't care about all the other pins. So I just want only this AN0 to be configured as analog, and rest all the pins let it be digital. So I'm just going to choose this one right over here. You can see when I put the value 1110 to these 4 bits, I will be configuring analog pin 0 as analog, and all the other pins will be configured as digital pins starting from AN1 to AN7. So I will be giving the value 1 to these 3 bits PCF G3 to G1, and I will be configuring PCF G0 to be 0. So for configuring the port of AD converter, I am just doing this ADCON1 bits dot G0 is equal to 0, ADCON 1 bits dot G1 is equal to 1, G2 is equal to 1, G3 is equal to 1. Port configuration. And nextly, coming to most important bit available in the ADCON 1, that is nothing but ADFM. So this bit is useful for selecting the result alignment format in address H and address L. So as I mentioned before, while I was explaining about the ADC peripheral of this microcontroller in the same video, I told that address L and address H are useful for storing the 10-bit ADC value, and these are the data registers. And each register is a 8-bit register, and in this register we will be receiving a 10-bit value. So let's take the 10-bit value that we got is the maximum 10-bit value 1023. So this 1023 requires 2 8-bit registers for storing, right? So the 1023 is nothing but 000000 1111111111. So this is the 1023. So we require at least 2 8-bit registers for storing this 10-bit value. Those 2 registers provided for us in this microcontroller is this address L and address H. So this result that we got in these two registers will be aligned in a particular format, and that alignment format can be selected using this ADFM bit. When I am selecting this ADFM to be 1, right justification method is selected, and when I am selecting the ADFM to be 0, left justification method is selected. Let me explain this in detail now. Let's take the value to be 1023 and the 1023 value is this one. And now when I am selecting the ADFM to be 1, as I said, right justified format will be selected. In right justified format, the MSB 2 bits of the 10-bit data will be stored in the LSB of the address H register, and LSB 8 bits of the data is stored wholly in the address L register. So this is the format of right justified, and when I set the bit to be 0, left justified is selected, right? So for left justification format, so this is the left justified format. Here you can see the LSB of the data, LSB 2 bits of the data is stored in the MSB of address L register, and MSB 8 bits of the data is stored wholly in address H register. So in this manner, the data will be stored when I am providing the value of ADFM to be 0. So I am just going to set the right justified format for further processing. You can choose left justified, but the mathematical operations did later in the process will be varying. So I am just going to set this bit to be 1, atcon 1 bits dot ADFM is equal to 1. You can see that's all about the configuration needs to be done for ADC peripheral. Next, moving to the reading portion of ADC value, I am just coming inside the while of 1 right over here. So the first process that we want to do is we just want to select the channel for reading the analog voltage data. That can be done by these 3 bits. CHS0 to CHS2 defines the channel for reading the analog data. So if these 3 bits are 000, channel 0, that is AN0 is selected, and if these 3 bits are 111, AN7 is selected. So in our case, we are just going to use analog channel 0. So I am just going to give 0 to these 3 bits. So atcon 0 bits dot 0 channel 1 is also 0, CHS2 is also 0. Sorry, 0 0 0. That means we are selecting channel 0, AN0. And after selecting the channel, you can see there is one important bit, that is go bar done bit. When this bit is made high, the ADC conversion will be started automatically, and when this bit is 0, the ADC conversion is not in progress. That is, it is automatically cleared by the microcontroller after the ADC conversion. So for setting this bit, I am just going to call this bit atcon 0 bits dot go bar done is equal to 1. Once initiated the ADC conversion, I am just going to wait till the ADC conversion is complete. So that can be done by checking for the flag called ADIF available in the PIR1 register. So here you can see an ADC conversion is complete when this flag is high. So until this flag becomes high, we are just going to wait here. So I am just going to write while PIR1 bits dot ADIF equal to 0. Until it is 0, I am just going to wait here. ADC conversion complete. So when it is complete, we are just going to exit this loop. That's all about the process that we are going to do. And once the ADC conversion is complete, we are just going to store the data onto a particular variable. So ADC value is the variable that I am going to declare. Unsigned int of ADC value. ADC value is equal to, as I said, I have aligned the data in right justified format like this. So here you can see when I am getting the maximum data 1023, I will be having 3 as the value for address H, that is 00000011 is the value 3, and here in this address L I will be having the value 255 because all the bits in this 8-bit registers are set. So when I directly add these two values, I will be getting the value 258, right? So 255 plus 3 will be providing the value 258, but that is not the value. Our value is 1023. So for that, what I'm just going to do is, I'm just going to take the address L register value and I'm going to put that onto a 16-bit variable. And after adding that to a 16-bit variable, I'm just going to left shift the address H value by 8 times, so that I will be getting the respective 8-bit values available in the 9th and 8th bit of the 16-bit variable. And then I will be taking the address L register and I'm going to add that directly to the 16-bit variable. So now you can see this is the 16-bit variable and this is the address L, and since this address L is a 8-bit variable, it will be adding the values of this address L directly to the LSB of this 16-bit variable, but the address H value is located in the MSB of this variable, so that it will not be affecting that value. So as I said, we are just going to take a 16-bit variable, that is nothing but ADC value. In our case, you can see unsigned int is a 16-bit variable, and I am going to store the address H value and I am going to left shift the address H value by 8 times. So address H left shift of 8, and after left shifting process, I am just going to add the address L value directly to the 16-bit variable. ADC value is equal to ADC value plus address L. And that's it. You can see now we will be having the 10-bit step value stored in this 16-bit variable ADC value. So in our process of this video, we have completed these 3 points, and finally we just want to display the step value onto the LCD. So that is the final step. We have successfully received the ADC step value and we have stored that to a 16-bit variable called ADC value, and finally we are just going to print that step value directly to the LCD available right over here, which is connected to port B of the microcontroller. So let's assume the value that we are going to print is 1023, which is the maximum step value. So we just want to split this ADC value variable into 4 characters for printing that to the LCD, because at the maximum the step value that we are going to receive is of 4 digits. So I am just going to declare several variables right over here: A, B, C, D, E, F, G. So ADC value variable is holding the number 1023. So that is our assumption. Now A is equal to ADC value divided by 10. So I am opening the calculator now for your better understanding. The value assumed is 1023 divided by 10 is providing me the value 102. So now A variable is holding the value 102. B is equal to ADC value modulo 10. And now 1023 modulo 10 is providing me the value 3, which is nothing but the last digit of the number. So B is holding the last digit of the 4 digits, and C is equal to A divided by 10. So A is nothing but 102. 102 divided by 10 is nothing but 10. So here also C will be holding the value 10, and D is equal to A modulo 10. So A is nothing but 102 modulo 10 will provide me the value 2. So D is equal to 2 is the result. So you can clearly see we got the third digit. Third digit is 2, right? So third digit is stored in the variable D, and E is equal to C divided by 10. So C is nothing but 10. 10 divided by 10 is 1. So I am getting the first digit. So C is holding the first digit. F is equal to C modulo 10. So C is nothing but 10. 10 modulo 10 is nothing but 10 modulo 10 is nothing but, sorry, here it is not C, it is E. So E is holding the first digit, and F is equal to C modulo 10. 10 modulo 10 is nothing but 0. So it is holding the second digit. So this is the order. You can see clearly E variable is holding the first digit, F is holding the second digit, D is holding the third digit, and finally B is holding the last digit. So I'm just going to print the number in this order to the LCD data of. Before that, I'm just going to give the command 0x8b for moving the cursor of the LCD to first row 11th column, and after that I'm just going to print E LCD data of F, LCD data of D, LCD data of finally B. And you must remember that all these numbers are available in integer format, but in our LCD we can only print data in ASCII format. So for converting this available data into ASCII format, we just want to add 0x30 to all these integer values. 0x30 is nothing but ASCII representation of number 0. So when you add that number, we will be getting the numbers converted into ASCII format. 0x30 plus 0x30. And that's all about the program. I'm just going to build the program now. You can see that's all about the programming logic that we are going to write. These are all the LCD functions that we wrote in the lecture of interfacing LCD with PIC16F877A in 4-bit mode, and I am not going to change this anymore. And these are the only things that I have written in this lecture, that is configured the ADC peripheral, and I have fetched the step value from the ADC peripheral channel 0. This is the configuration done for LCD that I have done in the one of the previous lecture itself, and this is the configuration done in this lecture. We have configured the ADC peripheral clock, and we have powered up the ADC, and we have configured the configuration bits for the ADC through these lines. And coming inside the while of 1, I have printed the port value in the first row first column of the LCD, and I have selected the ADC channel through this line, and I have started the conversion by setting the golden bit to 1. And here I am waiting until the conversion is complete. Once the conversion is complete, this line will be exited by the program, and after exiting, I am just storing the address H and address L value, that is the 10-bit value, to a 16-bit variable using some arithmetic operation. After storing the value to ADC value variable, Here I am splitting the ADC value variable and I am storing it to 4 different variables, and after that I am just printing that in a linear fashion so that the value will be printed from first digit to last digit from left to right. So this is the logic that we have built, and this process continues from here to here because these lines are written inside the while of 1, which is the infinite loop of the program. You can see the build is successful. So this is the logic. I am just going to build it again and I am going to run this program in the simulation. Double click on this microcontroller. I have already loaded the program file. Now when I play the simulation, you can see for 50% port value, I am receiving the value 511, which is approximately correct. Now when I vary the value and when I make it 0 by moving the knob towards the ground, it becomes 0. And when I move the knob towards the other extreme n towards the positive side, I will be getting the maximum 10-bit value 1023. And for all the intermediate voltage levels, I will be getting the respective step values between the range 0 to 1023. You can see, and it is finally 0. So our program is working fine. We have successfully interfaced variable resistor to the ADC channel of this microcontroller, and then we have printed the step value from the ADC peripheral directly to the LCD connected to port B of this microcontroller. For uploading the program onto the microcontroller, first power up the development board using 12V 1A adapter by this power jack provided in the development board, and then connect the PIC3 to the USB port of the PC using mini USB cable. And then the terminals of the PIC3 are connected to the microcontroller as per this circuit diagram. If your development board is not showing these pinouts, or if you are not having a development board, you can directly connect the terminals of the PIC3 to the microcontroller pinouts as per this circuit diagram. Or you can just build this circuit in a breadboard for programming the microcontroller. Once the circuit is built, click on this Make and Program Device Main Project icon in MPLAB X IDE. You can see the device is being programmed. Click on OK. You can see now the programming and verification is complete. That means successfully the program has been uploaded to the microcontroller. Now build this circuit to see the output in the hardware. Now that we have completed the connection between LCD and PIC16F877A microcontroller in 4-bit format, let's try to connect this variable resistor which we are going to interface to the PIC16F877A. So here you can see we are having totally 3 terminals in this variable resistor. So regarding this left terminal, I am just going to connect this leftmost terminal to the 5V of this development board, which is commonly sorted to the 5V of this microcontroller. And regarding the other extreme N terminal, that is this brown wire, I am just going to connect this rightmost terminal of the potentiometer to the ground of the circuit, which is the common ground between the microcontroller and this variable resistor. And regarding the middle terminal of this variable resistor, that is this blue wire, which is the sensing region for the analog sensor variable resistor, I am just going to connect this terminal to the RA0 of the PIC16F877A. So here you can see this is the port A and the first pin is the RA0. So I am just connecting this terminal to the RA0. You can see I have made the connection. So that's all about the circuit connections. We have successfully connected an LCD in 4-bit format, and we have connected a variable resistor to the RA0 of the PIC16F877A. And let's see the output in the hardware. Now you can see I am having the port value to be 0 because the knob of the potentiometer is placed in the extreme ground end. And when I rotate the knob of the potentiometer towards the other extreme end, you can see the port value increases based on the knob rotation of the potentiometer. And when I reach the other extreme end in the knob of the potentiometer, you can see I am receiving the maximum 10-bit value, that is 1023. So this is the output that I got in my hardware. So in this way, you can use the ADC channel of the PIC microcontroller for interfacing variable resistor or any analog sensor. And this is the output that I got in my hardware. See you in the next video. Thanks for watching.